Hello and welcome back to our next unit review video. Today we're going to review Unit 8, Radicals in the Quadratic Formula. Now this unit review video is going to be a little packed, so I'm going to try and not take too much time to go through each slide, so pause the video if needed to copy anything you need to. So here's a review video overview. We're going to have some topical reviews focusing on solving radical equations, basics about rational exponents, and simplifying radicals, and then the quadratic formula at the end. Here's the lesson overview for this unit. We had 7 lessons. Now we did revisit some of the topics in previous review videos, so the basic exponent properties, we're not going to review that in this video. That's when you have the same bases, you add the exponents, and so forth. Okay. So just review those in your notes. We're going to be revisiting or introducing the fractional exponents in this video and how it relates to roots. Okay, here are the Common Core standards associated with this unit. Please take a moment to pause the video and get a sense of them before we move on to the next ones. Okay. Here are the other Common Core standards associated with this unit, so please pause the video, just get a sense for them before moving on to the topical reviews. Let's look at some formulas. Okay. So the formulas for this unit deal with the rational exponent property, and that is when you have a base, say we have a base of x, and we have a fractional exponent like a over b. Okay. The numerator of that exponent is going to be considered the power, and your denominator, your b in this case, is going to be considered the root. So if you see an expression like x to the 2/3, that means your power is 2 and your root is 3, so you have the third root of x squared or the third root of x squared. So that says that this can be rewritten in 2 different ways. That x to the a to the b can be rewritten as the bth root of x to the 8th power, or the bth root of x all raised to the a. Now when you're evaluating expressions with fractional exponents, I think the second one makes a little bit more sense to use because you're making things smaller. You're taking the root first, making it smaller, then you're raising it to a power, instead of making it bigger and then taking the root of a larger number. It's easier, in my opinion, to work with smaller things first. The quadratic formula is another formula that you are going to be using in this unit. And this one is given to you on the Regents exam reference sheet, so you don't have to memorize it, but it's always a good idea to do it. Okay, so negative b plus or minus the square root of b squared minus 4ac all over 2a. And that's going to be used to solve equations of the form 0 is equal to ax squared plus bx plus c. Now, of course, we can solve some of those equations with factoring techniques and completing the square techniques, but quadratic formula always work because not every quadratic equation is factorable. So let's start looking at the basics of square root functions and their graphs. Now, it's important to point out that square root functions are actually inverses of part of a quadratic function. It's inverse of part of a quadratic function because if you look at a quadratic function, it's not one-to-one. It fails the horizontal line test at 2 different spots. Not 1, 2, 1. So therefore its inverse is not a function. However, if you just restrict the domain of a quadratic and you look at just the positive inputs, the positive domain, then you have a one-to-one part. Therefore it has an inverse. And it looks like this. Starts at the origin, and it looks like that. Okay. That's what the parent graph for a square root function looks like. So if f of x is the square root of x, that's what it looks like. The domain of your parent function is going to be all inputs that are greater than or equal to 0, and your range is going to be all outputs that are greater than or equal to 0. So x is greater than or equal to 0, y is greater than or equal to 0. To solve for the domain and the range, you're really looking to see how the graph shifts and is reflected. You're not worrying about the dilations, because the dilations, as you can see, keeps the point 0, 0 where it is, the domain and range stays the same. But as it's reflected through the x-axis, you get y values that are negative. Or if you reflect it through the y-axis, you get x values that are negative. So that affects the domains and range, the reflections. And of course, if you shift it up or down, then you end up getting a domain and range that's based upon where the graph starts. Okay. So the general idea for the domain, though, is to set what's under the radical greater than or equal to 0. Because if you think about it, you can't take the square root of a negative number, something less than 0, to give you a real result. You can take the square root of 0 or anything positive. So the only inputs that are allowed are all the x values that make what's under the radical greater than or equal to 0. The range, you're going to look at the reflections and the shifts. Just the vertical reflections and the shifts. Okay. Alright, so now for the domain and range of this first function, f, I'm going to first set x minus 2 is greater than or equal to 0. Notice I'm just dealing with what's under the radical, not the radical itself, which gives me a domain of x is greater than or equal to 2. Okay. If you think about how it's shifting, it is shifting to the right 2. That's what the x minus 2 means, so x is going to be greater than or equal to 2. For the range, it's dilated by a factor of 3, but there's no negative, so it's not reflected. It's just being shifted up 7 units. So you're going to take that y is greater than or equal to 0 and add 7 to it, so it gives me a y is greater than or equal to 7 for the range. And if you were to plot this in your graph, you'll notice that the graph starts at 2, 7, clearly indicating that the domain is all the x values greater than or equal to 2, and the range is all greater than or equal to 7. Now if you look at function g, for the domain, notice we have a quadratic underneath the radical, and that's okay. You're still going to set it greater than or equal to 0 to solve for the domain. But now we have a quadratic inequality instead of just a linear inequality, which means we have to, after it's compared to 0, factor it. Two numbers that multiply to 3 that add to negative 4 are negative 3 and negative 1, which now gives me critical values of 3 and 1. If I were to plot those on a number line just to see what's happening, and noticing that it's greater than or equal to, which means it's a disjunction, it looks like this. So my domain is going to be x is less than or equal to 1, or x is greater than or equal to 3. There's my domain. So notice the graph of this function is going to look a little different than the parent function, but it's going to look similar. It's going to have the same shape, just maybe in two different spots, because we have two different parts of the domain. Now if you look at the y's, shifting and reflecting, the dilation of 7 is not going to affect the y's, but the negative means there's a reflection through the x-axis, which means that it's pointing down, and then we went down 5. So for the range of this particular function, it's going to be y is less than or equal to negative 5. Less than or equal to because it was reflected to the x-axis, and negative 5 because it went down 5. And if you were to plot this in your calculator, you'll notice you get a graph that looks something like this. Now your calculator may not look exactly like that. It depends on what your window is and how far zoomed in you are. And your calculator can only plot certain points and then connect what it can plot. So your calculator might give you something like this. It only gives you like part of it. But really it looks like this function right here. And if you look at the table of values, it will verify that for you. If you look at your tables, you'll see at 1 you have negative 5, at 2 you have error, and at 3 you have negative 5. And you look at anything else, it's all negative. Okay, less than 5. Verifies your domain and range. Pause the video, write down anything you need to before moving on. Now let's look at solving radical equations. To do that, what we're going to do is we're going to isolate the radical, and then you're going to square both sides. because squaring is the inverse operation of taking the square root. Now, when you square both sides, however, it introduces the possibility of an extraneous root. If you have 9 equals 9, that could have come from negative 3 squared, or it could come from positive 3 squared. But obviously, negative 3 is not equal to positive 3. But if you were to square both sides, that will give you that 9 equals 9, a true statement. So squaring both sides introduces the possibility of extraneous roots. So you have to check your answers. So let's solve this first equation. We're going to get the radical by itself, so notice there's 4 added to it, so I'm going to subtract 4 from both sides. Leave me with radical 2 plus x is equal to x minus 4. And now notice how I'm going to be showing my work. I'm going to space my work appropriately so that my work is logical and orderly. Okay. So I'm going to square both sides now. The radical is by itself. Okay. Squaring the radical cancels the radical, leaving just 2 plus x. Squaring a binomial gives me x squared minus 8x plus 16. Now remember, if you forget the square binomial, you could always multiply x minus 4 and x minus 4 together. Notice this gives me a quadratic equation. So to solve this, I must make it equal to 0. So I'm going to subtract x from both sides and subtract 2 from both sides. Leave me 0 is equal to x squared minus 9x plus 14. Don't forget that equals 0. If you forget that equals 0, then you're missing part of your work. Now it's equal to 0, I'm going to factor it. Two numbers that multiply to positive 14 that adds to negative 9, or negative 7, negative 2. So using my zero product law, I get x equals 7 and x equals 2. However, now recall that because we squared both sides, we might have an extraneous solution. Means one of those values, or both of them, or none of them, won't work in the equation. So let's find out if we have 0, 1, or 2 solutions to this equation. We're going to check x equals 7 first, and I'm going to label this as x equals 7 so I can show clearly what I'm plugging in. And you always check into the original equation, so I'm going to plug it into that 4 plus the square root of 2 plus x equals x. So 4 plus the square root of 2 plus 7, I want to see if that's equal to 7. I plugged in x as 7. So 4 plus radical 9 equals 7. 4 plus 3 is equal to 7. That gives me a true statement. That's good. Okay, that means 7 does work in the equation, and it is a solution. Now let's check x equals 2, because that may work, they may not work. I have 4 plus the square root of 2 plus 2. Is that equal to 2? Plugged in a 2 everywhere there's an x. You might be able to see right off the bat this is not going to work, because 4 add to any number is going to give you something larger than 4, not less than 4. So you're going to clearly see that 6 is not equal to 2. So that means that x equals 2 is not a solution. We can cross that off. So our answer to this equation is just x equals 7. Now be careful about this, because if this were a multiple choice question, you might have 4 choices, and the Regents likes to do this, where you have one choice is x equals 7, next choice is x equals 2, because they usually try and line up the answer with the choice of the answer, and x equals 2 comma 7, or no solutions. Okay. They'll put this as a possibility for an answer. And what you'll have to know is that once you get down to the x equals 7 and 2, you first instinct will say, well, there you go, there's our answer. But obviously that's wrong, because we just found out that's wrong. The answer is just 7. So just be careful about that. Okay. Pause the video before moving on to the next equation. Okay, now some radical equations have 2 radicals in them. In that case, you want to isolate one of them, and then that would, when you square both sides, will eliminate it down to just 1 radical rather than 2 radicals. So then you'll have to continue the process again to get no radicals. But still check for extraneous roots, because by squaring you still might be introducing some extraneous roots. So I'm going to isolate actually this radical right here. Okay. If I isolate that radical, I'm going to get radical 2x plus 1 is equal to 2 minus radical x minus 3, because I subtracted the radical x minus 3's from both sides. I'm going to square both sides now, because that'll get rid of the radical on the left side, which gives me 2x plus 1. However, notice on the right side, when I square that, I have a binomial now that I'm squaring, which means the middle term is going to have a radical in it still. Okay? But just recall, if you have a binomial, some a minus b squared, that means you have a squared minus 2 times them multiplied together, plus the last one squared. Okay. So notice that b down below is your radical, so the radical will go away for this part right here, but it will remain in that middle term, so we'll have one radical. So when you square this binomial, the 2 squared gives you a 4. Multiply them, you get 2 radical x minus 3, but you have to double it, so it becomes minus 4 radical x minus 3. Then square the last one, squares the negative as well, becomes just an x minus 3. I'm going to go ahead and combine like terms to clean it up a little bit before solving it further. I notice that there's only one x term. 4 minus 3 gives me a 1, and I'm left with a minus 4x, radical x minus 3. Solving this further, I got to isolate this radical over here. So I'm going to subtract x from both sides and subtract 1 from both sides. Now notice in this case, the 1's cancel nicely, but they may not always. Okay. You may end up with a binomial on the left. And you just do what we did in the previous example. You square a binomial, you get a quadratic. Okay. Still get a quadratic when we square both sides. However, this time we're squaring just an x to give you an x squared. And on the right side, we square the negative 4 to give us the 16, and square the x minus 3 to give us x minus 3. So the radical goes away. That gives me the equation x squared is equal to 16x minus 48 when I distribute that 16 to both the x and the negative 3. And I'm going to move my work up here just so I have a little more room. It's a quadratic equation, so I have to make it equal to 0. Subtract the 16x from both sides and add the 48, and I get this equation, which actually does factor nicely. The two numbers that multiply to positive 48 that add to negative 16 are negative 12 and negative 4. So that means I get x equals 12 and x equals 4 as my possible solutions. But let's check them. Check x equals 12. Now in this case we have a lot going underneath the radical, so it's okay to multiply the 12 by 2 to give you a 24 plus 1. Okay. Remember, you're checking the original equation. Plus radical 12 minus 3, is that equal to 2? So radical 25 plus radical 9, 5 plus 3, obviously that's not equal to 2. Okay, so that means that 12 can be eliminated. Okay, but it doesn't mean that 4 is going to be a solution. Let's check that. If you check x equals 4, notice you get radical 8 plus 1 plus radical 4 minus 3. See if that's equal to 2. I just multiply the 2 and the 4 to get the 8. Okay. Radical 9 plus radical 1. 3 plus 1 is equal to 2. Nope, that's false. 4 is not equal to 2. So that means that 4 is not a solution. So that means the solution to this problem is no solutions. Okay. It's weird to think about that. Solution is no solutions. It's possible. With these radical equations, you might get situations where you have no solutions, like here. One solution is like the last problem, or both solutions will work. Pause the video, write down anything you need to before moving on. Now let's look at some rational exponents. So remember, the rational exponent property says if you raise a base to a fractional exponent, then you can write it as the bth root of that power, all raised to the 8th power. I'm going to use this one rather than the other one because it's going to be easier to deal with roots raised to a power than it is powers taken as root of them. Okay. So if I'm asked to evaluate 32 to the negative 4/5 to find out what that's going to be equivalent to. I don't want to find necessarily the decimal approximation because it might not be a nice decimal. I want to find it in simplest fraction form. Now, I may note the negative exponent here means that it's going to turn into a positive if I put it in the denominator. So I'm going to do that first. Right? 1 over 32 to the 4/5. That 4/5 means that the 4 is the power, the 5th is the root. So I'm going to rewrite that as the 5th root of 32 raised to the 4th power. Now in your calculator, you can calculate what the 5th root of 32 is. Because if you hit the 5, the 5th root, then go to math, and on my calculator the 5th option is x root. Okay, that's going to take the 5th root. So you type the 5 in first, then x root, and then type in 32. In my calculator with the TI-83 Plus, I'm not going to put parentheses because it didn't start parentheses. I'm just going to put 32. Hit enter, that gives me 2. So this, the 5th root of 32, is 2. So this becomes 1 over 2 to the 4th. 2 to the 4th is 16, so 1 over 16. That's going to be my reduced fraction, my reduced form of 32 to the negative 4/5 power. Now let's look at the next one. We're evaluating a function dealing with fractional exponents. So we want to find f of 8. So we have to plug 8 in everywhere there's an x. So we have 6 times h to the 2/3 power minus, and I'm going to write this as 1 over 12, because 12 to the negative 1 is 1 over 12 to the 1st. Okay. Let's make that a positive exponent just to deal with. Alright, now let's find out the 2/3 power of 8. So it's the cubed root of 8 raised to the 2nd. Now the cubed root of 8, you may know already, is 2. Okay. Because 2 times 2 times 2 gives you 8, so the cubed root of 8 must be 2. So this becomes 6 times 4, because 2 squared is 4, minus 1/12. Okay, we'll reduce this in simplest form, so 24 minus 1/12. Common denominator, so I have to multiply the 24 by 12 over 12. That gives me 288 over 12 minus 1 over 12. So my answer in simplest form is 287 over 12. Now if you wrote that in your calculator and typed it in, you would have gotten something like 23.916666666. So if you write in a decimal answer, make sure you put the bar above that 6. Okay, they're equivalent. Alright, now let's look at expressions involving fractional exponents. So when you have something like this, you want to make sure that this whole expression, because it's raised to a power, that this 1/3 gets distributed to each part of the parts in parentheses. So you can rewrite this as 8 to the 1/3. Multiply the exponents, so 8 to the 1st. Then the next one's going to be x to the 4/3, because 4 times 1/3 is 4/3, times 6 to the y to the 6/3. Reducing this further, 8 to the 1/3 is the cubed root of 8, which is 2. X to the 4/3, well, I can't reduce any further, so it's x to the 4/3. But 6 over 3 is 2, so it's going to be y squared. There's your expression in simplest form. Now let's look at something a little more complicated. We have a lot of variables here and a lot of numbers, okay? But we're noticing first off that everything is multiplied together in the denominator. So in that case, we know the 3's are going to cancel, because anything that appears in the top and in the bottom that are being multiplied together will divide nicely. 3 in the top, 3 in the bottom divides to 1. I also notice that this is a negative exponent, so I'm going to move it to the top. Okay. So I'm going to rewrite this now as x to the 2/3 y to the 1/4 over 4. Now I'm noticing now there's 2 y terms in the bottom. I'm going to combine those. If you combine those, you have to add the exponents because you're multiplying the same base, which gives you y to the 4/2, so that's y squared. Now I'm noticing I still have two y terms, so since one's on the top, one's on the bottom, I have to subtract the exponents to find out what goes on the top. 1/4 minus 2, which is minus 8/4, gives me negative 7/4. So this reduces down into x to the 2/3 y to the negative 7/4 all over 4. But I don't like to have negative exponents in my final answer, so I'm going to move it to the bottom to give me a final answer of x to the 2/3 all over 4 times y to the 7/4. That's my final answer. It's a little messy, but that's our final answer in reduced form. Reduced form should always have one variable, okay, either in the top or the bottom, and only positive exponents. Alright, pause the video, write down anything you need to before moving on. Okay, now simplifying radicals, what you want to do is you want to look at the perfect squares or the perfect cubes or the perfect fourths, depending on which route you're taking. Okay. And you always want to break it up into two radicals. One radical contains the perfect squares or roots, third roots or fourth roots, perfect fourth and so forth, and the other one doesn't contain perfect. You want to find the highest one that divides into each. For the perfect squares, those are the ones we're most familiar with. The highest perfect square that divides into 72 is 36. So I'm going to put the 36 underneath one radical and the 2 underneath the other radical. Now for the variables, the only way a perfect square is a variable's perfect square is if it has a power of 2. A multiple of 2 is a power. So I have a to the third, that's not a power of 2, but the highest one is underneath there is a squared, which means I have an a left over. 8 is a multiple of 2, so it is a perfect square, so I don't have to do anything other than just write b to the 8th in the perfect square radical. C to the 5th is not, because it's not a multiple of 2, but the highest one is a c to the 4th, so I still have a c left over. Reducing this, I'm going to reduce everything that I can. So the radical that can simplify, I'll simplify. Radical square root of 36 is 6, square root of a squared is a, square root of b to the 8th is b to the 4th, square root of c to the 4th is c squared, and I'm left with radical 2ac. Is my simplest radical form. For the cubed roots, you have to deal with the perfect cubes. So let's just refresh ourselves. 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64. Okay, so I can stop there. But I could go further if I knew I had a larger number than 54. Okay, to get like 125 and then 216 and so forth. Okay, but the highest perfect cube that divides into 54 evenly is 27. So I'm going to break this up into two cubed roots. One's going to have a 27 and one's going to have the remaining 2 that's left over. For the cubed roots, the variables need to have multiples of 3. For the fourth roots, they need to have multiples of 4. So in this case, cubed root, we have x cubed, x to the 6th, x to the 9th. Those are all perfect cubes. So x to the 8th is not a perfect cube then, but the highest one is x to the 6th. And I have an x squared left over to make an x to the 8th. Notice in this one that doesn't simplify, whatever exponent you have must always be less than the root that you're taking. So if you got x to the 4th underneath the radical, that means you can simplify it further. So just be aware of that. Okay. Let's simplify this first radical. Cube root of 27 is 3. Cube root of x to the 6th is x squared, because 6 raised to the 1/3 power is 6 times 1/3, which is 2. And then I'm left with a cubed root of 2x squared. Now be careful when you write your final answer, especially with the cubed roots, fourth roots, and so forth, that this little cube is clearly a root and not a power. It's very easy to make it look like a power. So make sure it's nestled into the square root sign really nicely. Okay. Now for the fifth root, I'm going to use the same kind of process, but this time I'm going to be dealing with perfect fifths. So for the perfect fifths, 1 to the 5th is 1, 2 to the 5th is 32, 3 to the 5th is 243. Okay, I can stop there, because I know I'm not going to have 243. It's much larger than 96. So I'm going to break this into two perfect fifths. The highest one that divides into 96 is the 32. You notice it goes in 3 times. So 32 is a perfect fifth. For the variables, I'm going to have multiples of 5 as a power, so x to the 5th, x to the 10th, x to the 15th. So x to the 11th is not a perfect fifth, but x to the 10th is. So 16. X to the 10th is, and we're left with an x left over to make x to the 11th. For the y's, y to the 6th is not a perfect fifth, but y to the 5th is, and I'm left with a y. Let's reduce this. Fifth root of 32 is 2. Fifth root of x to the 10th is x squared. 10 to the 1/5 is x to the 10 times 1/5 is 2. And then we have y. And then we have fifth root of 3x, y. Again, make sure that your root is clearly a root and not an exponent. Pause the video, write down anything you need to before going on to the quadratic formula. Okay. Now, the quadratic formula is going to be given to you. You just need to know how to apply it. And it's usually applied when you're asked to find the zeros of a function, or when you're solving a quadratic equation that's not factorable. Okay, but here we're finding the zeros of the following functions. And we call that zeros are anywhere that the function has an output of 0. So we don't have to rewrite this equal to 0. We know our a is going to be 1, our b is going to be 6, and our c is negative 12. So when you're doing this, you have to plug it into the formula completely. Don't just simplify it as you go along, but plug everything in. So I'm going to write the negative 6 plus or minus the square root of, in parentheses, 6 squared minus 4 times 1 times negative 12 all over 2 times 1. Put the parentheses there, especially when you have the negatives. Make sure that you square the negatives appropriately and multiply them appropriately in your calculator. Now my suggestion is to look what's underneath the radical and just type what's under the radical in your calculator just to get one number. Okay. When you type that in, you'll see you'll get 84. So we have negative 6 plus or minus the square root of 84 over 2. And 84 is not a perfect square, however, it can simplify because 4 goes into 84 21 times. So we get negative 6 plus or minus radical 4, radical 21, all over 2, which simplifies to negative 6 plus or minus 2 radical 21 over 2. Now at this step you might be done, but I'm noticing that the 6, technically the negative 6, the 2 and the 2, all three of those terms have a 2 that's in common that it can be reduced by. So if I divide each of them by 2, I get negative 3 plus or minus 1 radical 21 over 1. And because it's equal to, because it's over 1, my final answer is going to be negative 3 plus or minus radical 21. Sometimes you might have your answer as a fraction. Sometimes it reduces nicely like that. Okay. There's our answer. Now, of course, the question may ask you to find the zeros rounded to the nearest hundredth. In that case, you type in negative 3 minus radical 21 and negative 3 plus radical 21 in your calculator. And in doing that, you find that x would therefore be approximately negative 7.58, and x equals positive 1.58. So just be careful about how the question's wording you to write your answer as. Now let's look at this next one. Now this one deals with a lot of high numbers, so let's hope that this turns out to be really nice. We don't want to do a simplest radical form of a really large number, but we're going to plug it into the quadratic formula because it's going to be equal to 0 to find the zeros. So our a is 10, our b is negative 9, and our c is negative 91. So we get positive 9, because negative 9 is positive, plus or minus the square root of negative 9 squared minus 4 times 10 times negative 91 all over 2 times 10. Now plugging that bit underneath the radical, you'll find that it reduces down to 3,721. It's a really large number, right? Let's hope we don't have to simplify that using simplified radical form. Now, especially with a number that large, just type that in your calculator to see if it is a perfect square. If you get an integer, it is. And it turns out that it reduces down to 61. So we don't have to worry about simplest radical form because that simplifies to just a 61. Now I'm not going to leave my answer like this, even though it can't reduce the 9, the 61, and the 20 have no common factors. I'm going to, since I have the plus or minus and no radicals, I'm going to separate my answer into two parts. The lower one's going to be the 9 minus the 61 over 20, and the larger root is going to be 9 plus 61 over the 20. Okay. So reducing this further, we get negative 52 over 20 on the top, which reduces by a factor of 4 to give negative 13 over 20. And the bottom is 70 over 20, which reduces by a factor of 10 to 7 over 2. So our answers to this one are going to be negative 13 over 20 and x equals 7/2. Now these are nice, but, oh sorry, not negative 13 over 20, negative 13 over 4. Hopefully you caught that. Or 5, should I say 5. Negative 13 over 5. Okay. Hopefully you'll see that those are nice decimal answers as well. So you could have written your answer as x equals negative 2.6 and x equals 3.5. That's perfectly acceptable as well because they're exact answers. Okay, but fractions are sometimes nice to leave your answers as. Pause the video now and write down anything you need to before moving on to our summary. Okay, here's the most important things you should be able to take from this unit. Okay, you should be able to graph a square root function and identify the domain and range of a square root function given its equations. You have to look at the reflections and the translations of the function. And the domain is going to be anything underneath the radical must be greater than or equal to 0. You should also be able to apply the rational property of exponents to convert between exponential and radical form. Okay, solve radical equations, noticing that you could have extraneous roots because the operation of squaring introduces the possibility that you have extraneous roots. You should be able to simplify radical completely. Doesn't matter if it's square root, cubed root, fourth root, fifth root, sixth root, okay, by looking at the perfect squares, perfect cubes, and so forth. And being able to apply the quadratic formula to solve a quadratic equation. I hope this review has been helpful for you, and I look forward to seeing you in the next video. Thank you for watching.